Section: Introduction. In this section, we explore the advancements in autoregressive mixed-modal foundation models, which have shown great potential in handling inputs and outputs that involve different types of data, such as images and text. These models excel in various tasks, including answering questions about images and generating content that combines multiple modalities, thereby enhancing AI's ability to understand and engage with our diverse world. While many mixed-modal models use a design that combines separate encoders or decoders for each type of data, this can restrict the model's ability to merge information from different sources and create content that blends these modalities effectively. To overcome this issue, Chameleon has introduced a unified transformer architecture that predicts the next token in sequences made up of both image and text tokens. This allows for smooth reasoning and generation across different types of data. Chameleon has been trained on around 10 trillion mixed-modal tokens and has shown impressive capabilities in various tasks, outperforming commercial models like Gemini 1.0 Pro and GPT-4v when it comes to generating long-form mixed-modal responses. However, scaling these early fusion mixed-modal models to larger sizes poses significant computational challenges. To tackle these challenges, we examine the use of routed sparse architectures, which have previously proven effective in enhancing language and vision models, as well as in multimodal contrastive learning. Applying these architectures to early fusion mixed-modal models presents both unique opportunities and challenges. Our approach is guided by the understanding that different modalities, like text and images, have varying information densities and redundancy patterns. While we integrate these tokens into a single early fusion framework, we suggest optimizing this setup by adding modules that are specific to each modality. We call this idea Modality-Aware Sparsity, MOS, which helps models capture features unique to each type of data while still allowing for strong integration across modalities through shared parameters and attention mechanisms. Previous research, such as VLMO, BAIT3, and VLMO, has utilized a mixture of modality experts, MoMa, approach to train vision-language encoders and masked language models. We apply this sparse component to the mixed-modal early fusion language modeling context. Specifically, we use Chameleon as our base transformer architecture and introduce sparsity in two ways. 1. With. We implement a mixture of experts, MO, approach where tokens are directed through a set of specialized feed-forward blocks, experts, at each layer. We organize these experts into groups based on modality, ensuring that each group only processes tokens from its specific type while allowing for adaptive routing based on semantics. 2. Depth. We introduce a mixture of depths, mod, approach, where tokens can choose to skip certain layers of attention and feed forward computations. For both approaches, we use expert choice routing to balance the load and maintain a consistent computation graph, which is crucial for efficient training. We conduct thorough experiments that control for computational costs, comparing our proposed architecture with a dense baseline and various sparse alternatives. With a training budget of 1 trillion tokens, our Chameleon MoMa model, which includes 4 text experts and 4 image experts, achieves a significant overall reduction in computational costs, saving about 3.7 times the resources compared to the dense baseline while only slightly reducing throughput. In contrast, the standard expert choice MO with 8 mixed-modal experts achieves a 3 times reduction in computational costs under the same conditions, with a smaller decrease in throughput. When we combine the MoMa approach with MOD, resulting in Chameleon MoMad, we see an increase in computational savings to 4.2 times overall. However, the performance of the MOD model during autoregressive inference is affected by its sensitivity to routing accuracy, leading to lower performance compared to Chameleon MoMa. We also show that we can improve the performance of Chameleon MoMa using a technique we call modality untied upcycling. This involves starting with a sparse architecture that has 1 expert for each modality and enhancing the learning of the routing for each type of data. By training this initial model for just 10,000 steps, we achieve further reductions in computational costs while maintaining or even improving performance. Our main contributions can be summarized as follows. we introduce the mixture of modality-aware experts, MoMa, for mixed-modal early fusion models, which allows for more efficient use of parameters. We explore sparse scaling in both the width and depth of transformers, showing that significant improvements in training speed can be achieved in each area. However, effectively combining these two strategies for better performance in an autoregressive inference context remains a challenge for future research. Additionally, we present the modality untied upcycling technique that enhances the efficiency of our sparse architecture. We provide extensive empirical results in analysis, shedding light on the scaling behavior and efficiency gains of our approach. Section Summary. In this section, we discuss the advancements in autoregressive mixed-modal foundation models, particularly focusing on Chameleon, which utilizes a single transformer architecture for effective reasoning and generation across text and image modalities. We introduce our novel approach, Mixture of Modality-Aware Experts, MoMa, which optimizes parameter allocation and enhances efficiency in mixed-modal early fusion models, while also exploring the challenges and benefits of applying routed sparse architectures to improve performance and scalability. Section Model. In this section, we describe our model, which is based on the early fusion architecture introduced by Chameleon. This architecture represents images and text as a series of discrete tokens within a single transformer framework. The main feature of Chameleon is its transformer-based model that uses self-attention mechanisms to analyze the combined sequence of image and text tokens. This setup allows us to understand complex relationships both between and within different types of data. We train the model using a next token prediction approach, which means it learns to generate text and image tokens one after the other. In Chameleon, images are converted into tokens using a learned image tokenizer that transforms a 512 by 512 image into 1024 discrete tokens from a codebook of 8,192 tokens. Text is tokenized using a byte pair encoding (BPE) tokenizer, which has a vocabulary of 65,536 tokens, including the 8,192 image tokens. This unified method of tokenization enables our model to handle any sequence of mixed image and text tokens. By using this early fusion method, our model gains several important benefits. 1. Unified representation. We create a shared space for images and text, which helps in reasoning and generating content across different modalities. 2. Flexibility. Our architecture can manage any combination of images and text, making it suitable for various tasks like image captioning, visual dialogue, and generating documents that mix both modalities. 3. Scalability. The token-based approach allows us to process both text and image data uniformly, which makes it easier to scale up to larger models and diverse datasets. This is supported by Chameleon's successful training on around 10 trillion mixed-modal tokens. 4. End-to-end learning. The entire model is trained in one go, allowing us to optimize both the representation and the performance for specific tasks together. Building on this foundation, we introduce techniques that focus on modality-aware sparsity to improve the efficiency and performance of early fusion models. These techniques aim to tackle the computational challenges of scaling while keeping the strong cross-modal reasoning abilities intact. Next, we discuss our width scaling approach, which incorporates modality-aware block sparsity in the feed-forward module, extending the standard mixture of experts (MO) architecture. The idea behind this approach is that tokens from different modalities have unique characteristics and information densities. By forming separate expert groups for each modality, we enable the model to create specialized processing pathways while still being able to combine information from different modalities. We organize the experts in each MO layer into distinct groups, with one group dedicated to processing text tokens and another for image tokens. This separation allows each group to focus on features that are relevant to its specific modality. By implementing modality-aware block sparsity, we aim for several advantages. 1. Improved efficiency. By directing tokens to experts that specialize in their modality, we reduce the computational burden of processing tokens with experts that are not suited for them. 2. Enhanced specialization. modality-specific expert groups can develop more refined features that are relevant to their respective modalities. 3. Maintained cross-modal integration. Even with the separation into modality-specific groups, the model can still integrate information across modalities through shared self-attention mechanisms in non-Mo layers. We also adopt a token-based routing mechanism. For an input token, our routing process occurs in 2 stages. First, tokens are routed to their corresponding modality-specific expert group based on whether they are text or image tokens. Then, within each modality-specific group, tokens are routed to specific experts using a learned routing function. We use a projection matrix to calculate the affinity scores between tokens and experts, following established Mo methods. Within each modality group, we implement expert choice routing, where each expert has a fixed capacity and processes the top tokens in a batch. We determine how many tokens each expert can handle based on the total number of tokens in the batch and a capacity factor. This approach ensures balanced utilization of experts during training and eliminates the need for a separate load balancing loss term, leading to a more stable optimization process. However, expert choice routing can disrupt causality in autoregressive language modeling since each expert selects the top tokens based on scores across all tokens in a batch. To address this, we use a combination of techniques. We apply a sigmoid function in the router scoring, allowing independent calculations of token to expert affinity scores. Additionally, we introduce auxiliary routers that predict the likelihood of an expert selecting a token based solely on its hidden state representation. These routers are trained after the main model training and are used during inference to maintain causality. In summary, the MoMa module for an input token can be defined in a structured way, and we apply residual connections and normalization after the MoMa computation. Our experiments, which we detail in later sections, show that the MoMa significantly enhances both efficiency and performance compared to dense baselines and standard Mo architectures. Section Summary. In this section, we describe our model based on the early fusion architecture of Chameleon, which integrates images and text as discrete tokens within a unified transformer, allowing for effective cross-modal reasoning and generation. We introduce a width scaling approach with modality-aware experts to enhance efficiency and specialization in processing different modalities, while maintaining the ability to integrate information across them, ultimately improving performance compared to traditional architectures. Section: Mixture of Depths. In this section, we further explore the idea of adding sparsity in the depth dimension of our model. Previous research has looked into achieving sparsity in depth using methods like randomly dropping layers or using learnable routers. We choose to focus on learnable routers and incorporate a new technique called mixture of depths, or MOD. Specifically, in each MOD layer, we apply the MOD technique before any routing occurs with mixture of experts, ensuring that it is applied to the entire batch before we split it by modality. For each MOD layer, we utilize a projection matrix to calculate the affinity score between tokens and layers. This is followed by applying a sigmoid function to the result. Similar to how we select experts in mixture of experts, we set a fixed number of tokens, denoted as K_D, which we choose from the top scoring tokens in a batch. We determine K_D by multiplying the batch size by a capacity factor, C_D, which we select based on empirical observations. In practice, we first fix the interval for the MOD layers and the capacity factor, then adjust the total number of transformer layers to ensure that the new architecture maintains a similar computational load per token as the original design. During inference, we cannot directly use the expert choice routing for mixture of experts or the layer choice routing for MOD, as selecting the top tokens within a batch disrupts the causal flow. To maintain causality during inference, we introduce auxiliary routers that predict the likelihood of a token being chosen by an expert or a layer based solely on its hidden representation. For each Mo layer, we create an auxiliary router that uses a sigmoid function applied to a CLU activation, which is calculated from the token's representation. Similarly, for each MOD layer, we introduce another auxiliary router with the same structure. We adopt a two-stage training process, where we first train the main model until it converges. After that, we train the auxiliary routers using a binary cross-entropy loss, guided by the actual top K routing assignments calculated over the entire batch. During inference, we only use the main routers to generate weight values, and we route tokens to an expert or layer based on whether the auxiliary router score exceeds a threshold of 0.5. When training mixture of experts architectures with learnable routers from scratch, we face unique challenges in optimizing both the representation space and the routing mechanism. We realize that the routers are responsible for dividing the representation space for each expert, but this space is not optimal in the early training stages, which results in a poorly trained routing function. To tackle this issue, we propose an upcycling approach. We start by training a model with one feed-forward network expert for each modality. After a set number of training steps, we convert this model into an expert choice mixture of experts module, initializing each expert with the previously trained expert from the first stage. We reset the learning rate scheduler while keeping the data loader state from the earlier stage, ensuring that the second stage training uses updated data. To encourage expert specialization, we enhance the mixture of experts routing function with gumbel noise, which allows our router to sample experts in a differentiable manner. This is done using a gumbel sigmoid function that combines the token score with independent samples of gumbel noise. Our upcycling approach, along with the gumbel sigmoid technique, helps us overcome the limitations of learned routers and improves the performance of our modality-aware sparse architecture. In practice, we find that a brief initial training period of 10,000 to 20,000 steps significantly boosts the efficiency and stability of model training, aligning with previous findings. Section Summary. In this section, we explore the integration of learnable routers with the mixture of depths, mod, technique to enhance sparsity in the depth dimension of our model. We propose an upcycling approach that begins with training a simpler architecture and then transitions to a more complex mixture of experts, MO, setup, utilizing gumbel noise to improve expert specialization and overall model performance. Section: Efficiency Optimization. In this section, we discuss how we optimize efficiency for the distributed training of mixture of modality-aware experts, or MoMa. We utilize fully sharded data parallel, FSDP, as our framework, but we encounter specific efficiency challenges that differ from traditional mixture of experts, MOs. We will outline these challenges and our solutions. First, we address load balancing. In our system, we can experience load imbalance because the ratio of text-to-image tokens can vary greatly across different GPUs and training iterations. This imbalance can lead to delays, known as the cascading straggler effect, which slows down the prefetching of weights for later layers and the release of gradients from earlier layers. Consequently, the overall training time is limited by the longest processing time for text and image experts across all GPUs in a batch. To tackle this, we created a balanced data mix that aligns the text-to-image ratio with the expert ratio on each GPU, which helps ensure load balancing on average. While we could use other rebalancing methods, like redistributing tokens at each feed-forward network layer, these might add extra communication overhead. Next, we explored efficient execution of experts for different modalities. One strategy we considered was to use homogeneous experts across modalities, meaning we would not route text tokens to image experts or vice versa. This allows us to process all tokens and modalities at the same time, as long as all experts handle the same number of tokens. Alternatively, we could improve efficiency by using block sparsity, which provides similar advantages without needing a perfect balance of expert tokens. We also thought about running experts from different modalities one after the other when the number of modalities is limited. This sequential approach allows us to better overlap computations from previous modality experts with the weight prefetching for the next ones, reducing memory pressure and removing the need for expert load balance assumptions. Since our experiments involve a large number of tokens per GPU, we find that hardware utilization is not a significant issue, even with multiple batched matrix multiplications. Therefore, we believe the sequential method is a clean and flexible option for our current experimental setup. We also implemented several additional optimizations to boost throughput. These include general optimizations like quantizing gradient communication and automatically fusing GPU kernels, as well as graph optimizations using a tool called Torch, Compile. Moreover, we developed specific optimizations for MoMa, such as reusing modality token indices across different layers to reduce synchronization between the CPU and GPU. We also streamlined the communication of per-layer statistics and moved these operations off the critical training path. For our setup, we used the same pre-training dataset and pre-processing as previous work. To evaluate scaling performance, we trained all models with over 1 trillion tokens. Unless stated otherwise, we set the sequence length to 4096 tokens and the model parallel size to 1. Our training process included a peak learning rate of 0.0001, a warm-up period of 4,000 steps, and a linear decrease of the learning rate to 1% of its peak value. In all Mo architectures, we implemented Mo in every layer, setting each expert's training capacity to the total batch size raised to the power of the number of modalities divided by the number of experts, ensuring that the floating point operations per token were comparable to the base dense model. In mod architectures, we applied mod in alternating layers, starting with layer 0, using a layer capacity factor of 25%. To maintain parity in floating point operations with the base dense model, we increased the total number of layers while keeping the hidden dimension constant. We provide detailed configurations for our dense and sparse models in a table, and additional pre-training details can be found in the appendix. For model comparison, we report training losses. Since our training budget of 1 trillion tokens covers less than one complete pass through our extensive pre-training data, we use training loss as a stand-in for validation performance. However, we note that our expert choice routing in both Mo and Mod modules complicates the training loss calculation, as it considers the top proportion of tokens from a batch, including future tokens. We address this by reporting test time performances using auxiliary routers, which show that our results generalize to validation settings and causal scenarios. Finally, we present the scaling performance of various models across different compute levels, matching floating point operations to 3 dense model sizes, 90 million, 435 million, and 1.4 billion parameters. We focus on 2 key metrics: training loss and pre-training speed-up factor, which indicates how a sparse model can achieve the same pre-training loss as a dense model with the same floating point operations using only a fraction of the total operations. We also found that introducing modality-specific expert groups significantly enhances pre-training efficiency, especially for the image modality. For instance, the configuration with 1 image expert and 1 text expert outperforms the dense baseline. The image loss in this setup is nearly on par with that of a regular expert choice Mo model using 8 mixed modal experts, while the text loss remains notably higher, suggesting that parameter untying has a greater effect on the image modality. Increasing the number of experts within each modality group further improves model performance. The configuration with 4 text experts and 4 image experts consistently outperforms the 8 mixed modal experts across various scales, particularly in image loss. However, this comparison also shows a slight decline in text modality performance, indicating that processing text across more experts might be beneficial. Section Summary. In this section, we address the efficiency challenges of distributed training for mixture of modality-aware experts, MoMa, using fully sharded data parallel, FSDP, focusing on load balancing and expert execution strategies to optimize performance. We implement various optimizations, including modality-specific expert groups, which significantly enhance pre-training efficiency, particularly for the image modality, while also ensuring that our training setup and scaling performance are effectively aligned with our computational resources. Section: Mixture of Depths and Experts. In this section, we observe that using both the mixture of experts, Mo, and mixture of depths, Mod, as well as their combinations, leads to faster convergence of training loss. Our results, illustrated in a figure, show that when we add mod to the Mo_1T1I architecture, which we refer to as mod_Mo_1T1I, the model's performance improves significantly across different sizes. Additionally, mod_mo_1t1i performs similarly to or even better than mo_4t4i across various model sizes and types of data, suggesting that adding sparsity in the depth dimension can enhance training efficiency. However, we also notice that stacking mod and mo yields diminishing returns. For instance, when we add mod to the mo_4t4i architecture, the performance improvement is only slight compared to mod_mo_1t1i and mo_4t4i. This improvement is more noticeable in text data, while the gains in image data are less significant. These results indicate that future studies could look into combining width and depth scaling to boost performance in text data, while enhancing image performance may require exploring different strategies. Next, we conducted additional experiments to understand how scaling the number of experts affects performance. We examined two scenarios, one where we allocate the same number of experts to each type of data, balanced expert allocation, and another where we assign different numbers of experts to each type. We used a dense model and an expert choice Mo with 8 mixed modal experts, Mo_8x, as our baseline. In the balanced expert allocation scenario, we found that as we increase the number of experts, the training loss consistently improves. However, the loss patterns for text and image data differ. The text loss improves steadily with each doubling of experts, while the image loss shows diminishing returns when increasing the number of experts from 2 to 4. This suggests that the unique characteristics of each data type lead to different outcomes in sparse modeling. This aligns with our earlier findings, where separating modalities over 8 experts significantly improved image performance but not text performance, indicating that text data may benefit more from having a larger number of experts. In the imbalanced expert allocation scenario, we noticed diminishing returns when assigning more than 2 experts to the image data. Therefore, we tried configurations that allocated fewer experts to the image data and more to the text data. We compared 3 configurations, all with a total of 8 experts but varying the distribution between text and image, Mo_7t1i, Mo_6t2i, and Mo_4t4i. We found that giving more experts to a specific type of data generally improves its performance. However, assigning more than 4 experts to the text data also leads to diminishing returns. Ultimately, the training losses for the 3 configurations converge to similar levels. Given the better balance achieved with the balanced expert assignment and our pre-training data mixture, we chose Mo_4t4i as our best Mo configuration, even though Mo_6t2i had a slightly lower average loss. We plan to explore how to design sparse architectures that effectively utilize the unique characteristics of different data types in future work. We also looked into the impact of upcycling, as discussed earlier. Specifically, we examined the 2.3 billion parameter mod model, comparing the training dynamics of mod_mo_4t4i when trained from scratch versus when it was initialized from a mod_mo_1t1i checkpoint. To ensure a fair comparison, we adjusted the data loader and training steps to match the number of training steps already completed by mod_mo_1t1i, keeping the computational cost equivalent. We tested initializing the model from 10,000 and 20,000 steps. Our results, shown in a figure, indicate that the training curves for the upcycled models have been adjusted to reflect the computational cost of the initial stage. We experimented with 2 seed checkpoints, mod_mo_1t1i trained for 10,000 and 20,000 steps, respectively. Our findings reveal that upcycling further enhances model training, resulting in a 1.2 times gain in computational efficiency with 10,000 steps in the first stage and a 1.16 times gain with 20,000 steps. We notice that the performance gap between the upcycled models and the models trained from scratch widens as training progresses. Regarding the optimal upcycling period, our results show that both initializations outperform the base Mo model, with the 10,000 steps providing a 1.2 times speedup and the 20,000 steps offering a 1.16 times speedup compared to the model trained from scratch. This suggests that there is likely an ideal point for upcycling, where undertraining the seed model provides minimal benefits for router convergence, while overtraining it hinders future specialization. Based on these insights, we recommend upcycling from 10,000 steps. However, we hypothesize that the best number of upcycle steps may change when training exceeds 1 trillion tokens, and we plan to explore this further in future research on in-depth upcycling of our model. Section Summary. In this section, we observe that combining mixture of depths, MOD, and mixture of experts, MO, accelerates training convergence and enhances model performance, particularly for text modalities, while diminishing returns occur when stacking these methods. We also find that optimal expert allocation varies by modality, with upcycling from a pre-trained model significantly improving training efficiency, suggesting a potential sweet spot for the number of upcycle steps that merits further investigation. Section: Throughput Analysis. In this section, we analyze the throughput of our models. We found that sparse models often do not provide immediate performance improvements due to their increased complexity and the challenges of balancing data. To measure how our proposals affect training efficiency, we conducted a controlled experiment where we compared the training throughput of different architectures, including combinations of MoMa, mixture of experts, MO, and mixture of depths, MOD. We ensured that the architectures had the same number of floating point operations as a dense baseline model with 435 million parameters. Our experiments were carried out on 256 A100 GPUs, using a sequence length of 4096 and a batch size of 6 per GPU. We summarized the model throughput in a table. When we compared the expert choice MO model with 8 experts to dense models, we noticed that introducing sparsity resulted in a throughput decrease of about 9%. This reduction likely stems from the extra computations needed for routing decisions and synchronizing gradients across all experts, even though the floating point operations were equivalent. Conversely, when we ran experts sequentially by modality, we observed that the execution overhead was not significant, attributing most of the throughput loss of about 6% to the need for calculating token indices for each modality. We could potentially reduce this overhead by precomputing the indices and sharing them across each transformer layer. When we combined modality-conditioned feed-forward with learned routing, we saw a gradual decline in throughput as the number of experts increased, with an additional overhead of 11% when using 8 experts. This loss was similar to the 9% decrease we experienced when moving from the dense model to the MO with 8 experts. While combining MOD and MO yielded the best training loss in our experiments, it also introduced an estimated throughput loss of 15%. This loss is due to the additional router required for the depth dimension in MOD architectures, which adds complexity and can create bottlenecks. Moreover, when MOD is combined with MoMa, it may worsen system imbalance because the number of active tokens varies for each modality at each layer, straying from the expected token mix ratio in the dataset. This imbalance can hinder the efficient execution of MoMa, especially with larger model sizes. To address this, we could adjust the MOD routers to accept tokens based on the predefined token mix ratio, but we need to further investigate how this might affect model quality, which we plan to explore in future work. Next, we evaluate our models, including the 1.4 billion parameter dense model and various sparse configurations, on held-out language modeling data and downstream tasks. We report perplexity scores on subsets of OBELICS and Shutterstock, which were not included in our pre-training dataset. Additionally, we assess zero-shot performance on a set of common-sense reasoning tasks that are commonly used to benchmark pre-trained language models. We also selected several vision language task datasets and reported the perplexity of the correct outputs for cross-model comparisons, formatting the examples in a zero-shot manner. For common-sense reasoning, we evaluated our models on several text-only tasks that are standard for assessing the common-sense reasoning abilities of language models, such as PIQA, SIQA, Hella Swag, Wino Grande, Arc Easy, Arc Challenge, Open Book QA, and Bool Q. We scored the prompts based on each candidate's answer and calculated accuracy using the candidate with the highest score. In image captioning, We used the Karpathy test splits of MS Coco and Flickr 30K, reporting both text-to-image and image-to-text conditional perplexity. For visual question answering, we reported the perplexity of the correct answers on the test dev split of VQAV2. For all sparse models, we conducted a second stage of training for auxiliary routers and utilized these routers for causal inference, with details available in the appendix. Regarding interleaved data modeling, we found that the performance of the dense model and various MO configurations aligned with the trends we observed in pre-training loss. By adding one more image expert, the 1.4 billion parameter MoMa 1T1I model significantly outperformed the dense baseline on most metrics, except for image-to-text conditional perplexity on Coco and Flickr. Similar to previous trends, adding the image expert led to notable performance improvements in the image modality. Increasing the number of experts further enhanced performance, with the 1.4 billion parameter MO with 8 experts achieving the best image-to-text results. Additionally, this model performed exceptionally well on text-to-text tasks. The 1.4 billion parameter MoMa 4T4I model excelled in all conditional image perplexity metrics, with its text perplexity closely matching that of the 1.4 billion parameter MO with 8 experts across most benchmarks. Overall, the 1.4 billion parameter MoMa 4T4I model delivered the best results in interleaved data modeling. Section Summary. In this section, we analyze the training throughput of various sparse model architectures, including MoMa, Mo, and Mod, finding that while introducing sparsity generally incurs overheads due to routing and synchronization, certain configurations like running experts sequentially can mitigate these losses. We also evaluate the performance of our models on language modeling and vision language tasks, demonstrating that our MoMa 4T4I model achieves the best results in interleaved data modeling, particularly excelling in image-to-text and text-to-text tasks. Section: Mod Performance Regression. In this section, we discuss the performance regression observed in the 2.3 billion parameter Mod MoMa 4T4I model, as shown in our table. Despite having a better pre-training loss, this model underperforms compared to the 1.4 billion parameter MoMa 4T4I model across all metrics. Our analysis points to the auxiliary router's performance as the main issue. We also examined a smaller model, the 635 million parameter Mod MoMa 4T4I. Initially, we confirmed that using the training router and selecting the top tokens within a batch for inference allows the 635 million parameter model to outperform the 435 million parameter MoMa 4T4I model. However, when we added random noise to the training router selection, with a noise ratio exceeding 0.5%, the 635 million parameter model began to underperform compared to the 435 million parameter model. Achieving an error rate below this noise threshold is challenging for training the auxiliary router, indicating that we need to conduct further research to create a more robust approach for practical applications of MOD. On a different note, we found that MO models do not show the same performance regression during inference, suggesting they are less affected by router errors. This resilience is likely due to the MO model's multi-expert structure, which allows mis-routed tokens to be processed by other experts, thus retaining their information. In contrast, the MOD model's single selection switch per layer means that routing errors cannot be corrected, resulting in more significant performance loss. Next, we explore early fusion vision language models. These techniques have become popular in multimodal learning because they effectively capture interactions between different types of data right from the start. Notable examples include Perceiver I/O, which uses a fully attentional architecture to process various inputs like text and images, and NUA, which employs a 3D attention transformer for understanding and generating text, images, and videos. Another example is a causally masked transformer that learns from mixed modal documents on the Internet, demonstrating the scalability of this approach for large-scale pre-training. We utilize Chameleon as our base transformer architecture and show that incorporating modality-aware sparsity can further enhance its performance. In the realm of multimodal representation learning, BATE3 has introduced a versatile foundation model that excels in both vision and vision language tasks. It features a multi-way transformer architecture with expert modules tailored for specific modalities and employs a unified masked data modeling objective for pre-training on images, texts, and image-text pairs. We also note recent progress in sparse multimodal language models. The VLMO model proposes a vision language framework that efficiently scales using a sparse mixture of experts approach. It applies sparse MO to both vision and language networks within a unified framework, utilizing masked data modeling objectives for pre-training. VLMO demonstrates strong performance on vision language tasks while using fewer parameters per token than traditional dense models, reinforcing the effectiveness of MO training in multimodal contexts. However, we acknowledge some limitations in our current MoMa implementation. It relies on matching the token mix ratio in the dataset with the expert mix ratio in the model to ensure balanced load across GPUs. Despite this, minor imbalances can still occur since there is no strict limit on how much a batch can deviate from that ratio at the per GPU, per iteration level. We plan to address these improvements in future work. While expert choice routing helps with load balancing during training, it introduces additional challenges for auto-regressive language models during inference. Although auxiliary routers make up a small portion of the network's parameters, their importance is significant. In our study, we trained the auxiliary router after completing the entire network training, limiting this to a few thousand steps. Previous research has shown that it is possible to train these modules alongside the full network. Future investigations should focus on the architecture and training methods for auxiliary routers to prevent them from becoming a performance bottleneck and to ensure they generalize well across different data distributions. We also need to explore training mixture of depths architectures that include both auxiliary routers and the original model to ensure effective performance in causal inference scenarios. In our work, we only tested the basic formulation of MOD and its staged integration with MO, leaving the exploration of other MOD variations, such as Modality-Aware MOD, for future research. Additionally, we recognize that batched sequence generation with mixture of depths, MOD, is complex, as it involves dynamic shapes and updates to the key value cache for each layer, with certain sequences and layers potentially skipping different tokens. There is still room for optimizing the inference implementations for MOD models.